In this edition of the Regenerative Farming Toolbox, I will explain how we figured out that charcoal is good for soils, along with what we know about how char influences the soil. Archaeologists were studying in the Amazon region, and they discovered that human civilization, discernible by finding pottery and pollen from crops like corn and pumpkin, were concentrated in areas of very fertile earth, which they called terra preta and terra mullata. At first, they thought that these soils had formed naturally, but on further inspection they realized that all of these soils had been intentionally created by ancient humans for the purpose of farming. They figured this out because these large tracts of fertile earth had charcoal and ground up bits of pottery, as well as fish and animal bones, and other manure residues mixed with them. Some of the richest soils, now famous as terra preta, had up to 14% organic matter. The thing about soil organic matter is, the warmer and wetter the environment, the faster organic matter tends to get decomposed out of the soil and converted back into CO2 by microbes. This is why the good forest soil of the Amazon usually oxidizes into infertile dirt in just a few years when it is logged and farmed. But the organic matter in these terra preta soils is much more resilient. How can this be? Soil scientists figured out that this resilience to degradation in the rich terra preta soils is due to the presence of biochar, charcoal which is holding on to nutrients and providing a home for countless microorganisms. They estimate that this char organic matter can persist in the soil for thousands of years. For your information, the terra preta and terra mullata soils are found in Brazil, Bolivia, Ecuador, and Peru. Terra mullata soils are slightly less fertile than the terra preta soils. As I researched more about charcoal-rich soils, I also discovered that there are more soils that are formed this way by humans. For example, the soil type known as mollisite, which is in the Great Plains region of the United States. It was also formed by strategic burning that was done by the Native American tribes who managed these vast tracts of land. It is estimated that 40 to 50% of the carbon in these soils comes from char, and that the majority of the cation exchange capacity, that means the ability of the soil to capture and release nutrients, comes from the unique properties of the char in the soil. Imagine the Great Plains of North America with cycles of bison moving across the landscape, grazing, trampling, manuring, then a regrowth phase. At the same time, the tribes who managed that land incorporated periodic fires, which in combination of these two things over a few hundred years built the topsoil, in some places, to 3 meters thick. Thinking historically then, that abundant topsoil is what enabled the central U.S. to become the breadbasket of the world. But in just a couple hundred years, because of excessive plowing and bad water management, the very farmers who were feeding the world were also bleeding away that precious organic matter, causing it to dissipate back into CO2 in the air or run down into the Gulf of Mexico, which caused algae blooms and die-offs of ocean life. I once read in Acres magazine that, quote, "The loss of organic matter on the Great Plains alone has produced more atmospheric CO2 than all of the American motor vehicles ever produced." It is a sobering reality that the 3 meters of topsoil that once existed on the surface of the Great Plains has been reduced to a mere 30 centimeters, according to some measurements. So, what I've gathered from this is, on one hand, soil organic matter from char can persist for thousands of years, but also it can be eroded away by water runoff and mineralized away by excessive plowing. Do you think we can turn back the tide of time by using wiser methods to regenerate and revive worn-out soils? I do. Before I move to the next slide, I want to give an honorable mention to other human-made soils that are prized for their fertility. Plagen soils in the Netherlands were formed by using peat as animal bedding. Tombundu and Chitimene soils of Guinea and Zambia are located on sites of old villages and are also more productive than the surrounding savanna. You guessed it, all of these soils are found to contain biochar. So what is it about biochar that makes it so amazing for soil? Researching how biochar works was surprisingly complicated, so I'm going to start with a simple explanation and then move on to the more complex explanation of this topic. If you look at this picture, you can see that this charcoal, when magnified, is covered in pores that look just like the cellular structure and water transport veins that are part of the plant it came from. This porous shape means that charcoal has an enormous surface area in relationship to its size. This makes it like a sponge, amazingly efficient at absorbing and holding on to water. Also, it turns out, just like a damp dishwashing sponge, all those cracks and crannies are a great place for microbes, bacteria, prokaryote, and fungi to live and reproduce when biochar is in the soil. Unrelated to soil, biochar is used in water filtration for this same reason. Microbes, odors, and even dangerous heavy metals that contaminate drinking water just can't resist sticking to the outside of the charcoal when water passes through the biochar filter. Biochar also absorbs elemental nutrients that plants need to survive. Elements like calcium and magnesium dissolve out of rocks and enter water in the soil. Normally, plant roots slurp up these nutrients together with water. In very sandy soils, the challenge is that these nutrients tend to wash away when it rains. This is because sand is a large and not very bumpy soil particle, so water drains away instead of sticking to it. Smaller sized soil particles like silt and clay do a pretty good job of having calcium and magnesium adsorbed to them. This way, those nutrients are stored in the soil until they get pulled up into the plant's roots. The big challenge for most farmers is nitrogen. Calcium and magnesium have positive chemical charges, but water-soluble nitrogen compounds have a negative charge. Non-organic soil particles like clay also have a negative charge. Since negative charges repel each other, nitrogen compounds can't stick to the ordinary dirt particles, so they easily wash out of agricultural soils. Nitrogen is very important because without it, plants can't make that pretty green compound called chlorophyll. And without chlorophyll, they can't do photosynthesis. Only organic matter can hold on to nitrogen in the soil. As a form of organic matter, biochar is also very good at this. The challenge with soil organic matter is that soil microbes really like to eat it. And when they eat it, while a portion remains in the soil as a part of the microbe's body, a good portion of it ends up being respired right back into carbon dioxide. That's right, just like us, microorganisms breathe out carbon dioxide. But scientists discovered something really amazing about organic matter from biochar. It doesn't break down and disappear like ordinary organic matter. Instead, it is capable of staying in the soil for up to thousands of years. This obviously makes it a very attractive option for farmers who want to build the long-term fertility of their soil. Like I explained earlier, it is possible to abuse soil to the point that char even erodes away, but erosion is different than degradation because of microbes. If you want an explanation of how microbes degrade soil organic matter in order to free up nutrients, please watch my video titled Till versus No-Till, Pros and Cons. Moving on. When I first researched for this lecture series, I listened to an interview with Kelpie Wilson, who also makes great resources about biochar. She claimed that one study found that adding biochar to the soil caused total soil organic matter to double beyond the amount of biochar added. She said that the reason for this might have to do with biochar causing increased microbial growth. However, that's a pretty unbelievable claim to think that the organic matter in the soil would double. Because of this and other reasons, when I reviewed my lecture materials in preparation for making this video, I looked at this slide and I still had questions. My questions were, how is biochar able to last for thousands of years? In addition to the study cited by Wilson, similarly, I also found claims that terra preta is able to regenerate at a rate of 1 centimeter per year. These are incredible statements. So my next question is, how? What is causing this to happen? And can I make the kind of conditions so that the same thing happens on my farm? Dr. Koutspokas, a researcher whose interview I listened to, cautioned that field tests with biochar have been inconsistent. Some have had fantastic results and some haven't. So I really wanted to understand about this properly as much as I could. Since this video is already almost 10 minutes long, I will share what I discovered in my next video. Hopefully, before I move to Tanzania next month, I will also publish the video I am preparing that shows my own experiments with making a biochar kiln, making biochar, and charging it using animal dung.